0.25 to the 4 minus 0. So, you substitute here. Then what is 0.75 to the 0? 1. And 0.25 to the 0, you need to get it from your calculator. Now, this 4 factorial over 4 factorial, that cancels out. 0 factorial by definition is 1. So, that is how you get this first one. Okay? All right?
Yes.
Next slide. Okay, likewise probability x equals 1, just x equals 1. Okay, x equals 2, like that. All right. So I can move over, right? Move on to the next.
So the example is showing 2 patients got well from 4.
Exactly.
Probability would be 0.21 or 6 for those 2 patients to be well.
Yeah, for any two out of the, yes, not specific. We do not know. I mean, if you have 4 patients, and then chance that 2 of them will be well would be about 21%. Okay, see, that's like each person in random is 75% chance, but look,
2% is 21%.
my gosh, it goes down so much, 21%. So like if you give the drug, even if you have a 90% chance that the drug will be okay, but if you give the drug to 10 people, it will not be 90%. You know what I mean? For even for 4 of them to it will be much less. Yes, Sophia.
So if x is equal to 4, is that equal to 1, like the result?
Probability x equals 4. No, it will probability x equals 4 will be even less than 0.21. You are talking about x less than or equal to 4 will be.
Equal to 4.
Probability x equal to 4. We can do that here on the board. X equals 4 is what? Can I write it here? Perhaps. Let me see. Okay, is equal to, right? Oh, I'm not so good with this. I can do C and then superscript. Where is the superscript? Under font?
It's right there.
Where?
You can do on the board.
Just do it on the board.
Yeah.
Okay, but then it may not go on the. Okay, so 4 choose 4. Probability that x equals 4 is 4 choose 4, right? Times 0.7524 times 0.25 4 minus 4, correct? So then what is 4 choose 4? This is actually 4 factorial divided by 4 factorial times 0 factorial. Now this will be 0.75 to the 4. What is it? You need to get the calculator. This is 0.25 to the 0, which is 1 actually.
0.3164.
0.3164?
Yep.
Okay, that's hard to believe.
That's pretty small.
Right.
Yeah, but see, the other one is 21.
Yeah, that's
This is equal, so this will be like 1 times that times 1. 0.3164?
It is.
Right.
I'm thinking because of the chance of the success is not higher, like it is.
Yeah,
That's
that
why
doesn't
if
make
you
sense.
pick 4 out of 4, so it's less chance. Because it's only 75%, is not like
Yeah,
90%.
so, yeah, the reason is this, okay, probably, oh, okay, yeah. See, the thing is, because the success rate is 0.75, think intuitively, there's a higher chance of having more than half the patients getting well. 0.75 is like more than even 50%, right?
Yeah.
So x equals 2 is the halfway point, right? For 4 patients, out of 4 patients. So there is a higher chance that there will be more patients getting well than half the number of patients. Because success rate is 75%.
That's the success rate. So yeah, for sure. If you have x equals 2.1, 21% is the success value. If you put 4, you get 31%.
Yes, that has to be, and that is to be this.
75% is the limit. That's what you mean, right?
No, see, what I'm telling is because the success rate is more than 50%, there's a higher chance that there will be more than 2 patients getting well. 2 out of 4 means halfway.
Yes.
So, I mean 75% means there's a higher chance than 50%. So, you can expect more than half the sample to be getting well. So, probability of x equals 4 and also probability of x equals 3 perhaps will be more than 21%.
Is that between?
It
Is
is,
that 26 something? Okay.
yeah, I think, yeah, we can do it real quick here. So, this is 4 choose 3, 0.75 to the 3 times 0.25 to the 1, right? So, 4 choose 3 will be 4 factorial divided by 3 factorial times 1. So, 0.75. So, this will be like 4 times, right? Because
0.42.
0.42, that's high.
That's high.
Yeah,
That's going high.
that's like 42%.
Almost.
Yeah. So, I mean that makes sense, isn't it? It is 3 out of 4 is getting close to 0.75,
Yeah.
right?
Yeah.
Okay.
1.04, 21, yeah.
So, it goes up and then it goes 0.21 and then keeps on going up.
It's kind of far-fetched because if you have 4 out of 4, then you're getting 31%. But if you have 3, then you're getting 42%.
Which is, yes. So, the chart will be like it goes up and then down a little.
Yeah. That's kind of-
Yeah. And then see, this is like x equals 3, right? This is x equals 3. So, this is like 3/4 because you know you are sampling 4 patients.
4 patients.
So, 3/4, right? Isn't
There
it?
is no trend. I mean, it varies.
It varies, yes.
You can't say 4 out of 4 will be 100%.
No.
No.
It varies, but typically the peak will be around the mean value. Typically. Now, I will, in fact, we can come back to this and then mean value will be 3. We can see it.
Yeah, 4 times.
Okay? 4 times, exactly. 4 times p would be 3. We'll figure it out. Okay? All right? That is interesting. Okay, then. So, maybe I will complete it and then again put it on Angel. Okay? Let me go down to the next one. Okay, continued. Oh, they calculate this. Okay, so so these are the, I just put that, these are the exactly equal probabilities. Okay, so these are P, MF. Okay, now let's go into cumulative distribution function, CDF. Now, CDF is less than or equal to. Now, this is also an important probability. Okay, you have to keep on adding up to a point. Okay. Now, see, this picture is, I think, in the textbook. I think it's figure 6.2. Okay. Now, see, what I did was, now they calculated the PMFs in the previous slides, right? So, the middle column is PMF. Now, CDF, which is a cumulative. So, what happens? You have to keep on adding, right? Starting from the top. Now, probability that x equals 0, the first value is the same. PMF and the CDF are the same. Does it make sense? Second value means you have to add this to this, isn't it? Because x is less than or, this is like x is less than or equal to 1. So, x is less than or equal to 1 means it can either be 0 or 1. So, you can add this plus this to get that. Okay, likewise, x is less than or equal to 2 means it can either be 0, 1, 2. You can add all these 3, or these 2 are already added in here, right? Then you add these 2 to get this. Okay? So, that is in fact, you know, what I have shown in here is in red. Kira, you okay?
No.
No, okay. Let's say cumulative distribution function is probability that x will be up to a point. X is less than or equal to 1, x is less than or equal to 2.
So that's the second column?
Third column here, yes. So, now you start with x equal to 0, which is the lowest possible. So, for the lowest possible value, the probability mass function and the CDF, cumulative distribution function, are the same. Second one, probability, this is probability x less than or equal to 1. Is that okay?
Yeah.
Less than or equal to 1 means it can either be 0 or 1. So you have to add this plus this, and you will get this. Okay? And then less than or equal to 2 means you add all these 3, but since I have already added these 2, you can add this with this to get that. Okay? So I have shown the how you get 0.2617. See, let me just make this red. Oh, it's not becoming red, I don't know. Maybe those things don't apply for nodes. Okay? So that's how you get the cumulative. See, now in the picture, what is colored in blue is the cumulative. See, you have to add this plus this plus this
to get the
to get the cumulative probability. Okay, so x is less than or equal to 3 means there will be a value. See, 0.0039 is somewhere here. 0.04. Why is no? This is not correct. You know, this is, oh, you know what? This is actually cumulative distribution function. No, this is not right. Point.
That's the number.
The second one, yeah.
It is the
First column, but these are 0.2s.
Yes,
Yeah,
0.2109.
Oh, I was reading this, sorry. Okay, all right. Okay. Oh, this is 0. Okay, I got it. Okay, so probability that x equals 0 is really, really tiny, right? And x equals 1 is 0.0039. Okay, now I got it. And then x equals 2 would be 0.2109. Okay, and then once you add this, only you get this column. Okay, so this is actually PMF. Okay. So actually speaking, the shaded part is only the CDF. Okay. Okay. So cumulative probability, you know, again they are sort of, you know, sort of reinforcing here. So recall the probability that x is less than or equal to a certain value. So that is like the, you know, general definition. Okay. And it corresponds to the left tail of the PMF. Does it make sense? Left tail up to a point. Tail means, you know, the edges, right? Edges. So this is like the left tail. That would be like the right tail. Okay. So left tail up to that point is the cumulative distribution function. Okay. It's just, you know, ways of just visualizing, I think. Okay.
So does it relate to the negative skewed and positive skewed?
Well,
Because there you have, you know,
yes.
coming.
You could say that the CDF would be much less if it is left skewed, right? Left skewed means the hump is on the right.
So that would be positively skewed.
Yes, positively skewed. Yes. So left skewed means the hump is on the right.
Right.
So then the CDF on that part will be very small because there aren't that many. The frequencies are okay, and the CDF will increase more aggressively towards the right.
Towards the right. So
Yes.
the tail in case of CDF would always be on the left.
Yes, CDF will be always on the left. Yes, CDF is always the left tail probability. You can write it as, you know, in just ways of remembering. Okay. In fact, this idea will come in useful even when we do continuous random variables. CDF is a left tail probability. Okay.
So how would you apply this this trend? Like the CDF is always the left tail. Does it? There are any specific questions where you say, okay, CDF is tail. So does the question ask you, okay, where is the CDF trend in this graph?
Yeah. Well, see, actually, CDF finally will turn out to be the percentiles. What is meant by the 95th percentile? 95th percentile is the mark where 95% are below it. So that's a left tail probability. So CDF finally will be the percentiles. Okay, and you always describe a data set in terms of percentiles. Okay.
Right.
So you know, even SATs or something, if you are in the 98th percentile, that means you have beaten how many? 98%. Thank you.
Yeah, I'm gonna do this. That computer didn't have the software.
Okay,
So
you're come.
I'll just go down there and do it real quick.
Okay, all right. So that's what it is. So actually CDF is a very important concept, very useful one. Okay. All right, then let's go to the next one. And then okay, so cumulative probability function, we did this. You guys know what we are doing, right? Can I skip it?
Yes.
So x is less than or equal to 0 is this. X is less than or equal to 1. See
0 plus 1.
0 plus 1. You see how you get that? Okay. And then x is less than or equal to 2 means you have to add, you have to include 2 as well. Okay. So that's how it goes. Okay. Okay, now the expected value and the variance for binomials. Okay. Now remember the symbol for expected value, it is mu. We did that for any general discrete random variable in chapter 5. Okay. Remember mu formula, I think I put it somewhere here. Oh, here, right here. We learned these two formulas in the previous chapter. How to find mu and sigma squared for any general discrete random variable. Okay. Nice thing about binomial random variable is when you sort of when you substitute the values for the binomial, this mu, which looks a little complicated here, turns out to be NP. It's easy then. So mu turns out to be NP, sigma squared turns out to be NPQ. But see, now I think I have warned you guys somewhere only for the binomial random variable. So maybe I should make it red. So these easy formulas are only for the binomial random variable. Okay. For any general discrete random variable, you need to derive it using these two formulas. Okay. So now mu is NP. Mu is like the expected value. On the average, how much do you expect? On the, if you were to have 100 patients, on the average, how many would you expect to be getting well? N times P, which is 100 times 0.75, 75 of them, right? With our previous example. So that's how we got 3. See, the 3 was the peak, right? Because n equals 4, 4 times 3 fourths is 4's cancel out, you get 3. See, NP so this is mu. So on the average, you will expect about 3 patients to get well out of 4 patients who are given the treatment. That is why the peak, the probability is highest when x equals 3. Does it make sense? So that has the highest frequency. X equals 3 has the highest chance. You see, it agrees with our intuition, doesn't it? Okay, so these are the two formulas for binomial. Okay, and then yeah, so this is just how to substitute values. See, in here you get 3, which we did on the board there. Sigma squared is 0.75. That is a spread, how spread out. Okay, that is sort of like a theoretical thing. Now, and then sigma, of course, is the square root, right? Now, say sigma squared. See, why do we go from sigma squared to sigma? Sigma squared, the units for sigma squared are not as the same as the units for x. So that is why we square root it. Think in terms of x. I think I explained this. Think in terms of x in inches. If you have x in inches, the mu also will be in inches, but the variance will be in squared inches, because you have a x squared playing a role there. Okay, so to bring it back to the inch axis, you need to square root. So that is why that is why you have the sigma standard deviation. Let me see if I can copy that and do another one. So it is oops that did this. How do you do this lowercase? You can do the lowercase here, right? Can't you change from lower to upper? I think lowercase. It did not do it. Let me go here, insert symbols where?
There, next to it here, yeah.
Okay.
There it is.
thank you. Okay, I should go very carefully and then, okay, so it's square root, okay, square root of 0.75, which is what?
.866.
866, okay. So now in fact I'll just make a note in here, has the same units as x, okay, the random variable. So it can be marked on the variable axis. Okay, sigma square you cannot have squared inches in the inch axis, right? And then look here, so in here mu equals 3, see that has the highest chance, which you expect. Okay, all right, then let's go to the next one. Yeah, okay, here just a simple illustration. Does the observation of 2 success cast doubt on P equal to 0.75? So what you could do is, okay, you can find up to 2, what's the chance? The chance is 0.2617. So it is not 2 unusual.